You wrote a book about aliens. So the big question, how many alien civilizations are out there?
Yeah, that's the question, right? The amazing thing is that after 2.5 millennia of people yelling at each other or setting each other on fire occasionally over the answer, we now actually have the capacity to answer that question. So in the next 10, 20, 30 years, we're going to have data relevant to the answer to that question. We're going to have hard data finally that will, one way or the other, even if we don't find anything immediately, we will have gone through a number of planets. We'll be able to start putting limits on how common life is. The one answer I can tell you, which was an important part of the problem, is how many planets are there? Right. And just like people have been arguing about the existence of life elsewhere for 2,500 years, people have been arguing about planets for the exact same amount of time. Right. You can see Aristotle yelling at Democritus about this. You can see they had very wildly different opinions about how common planets were going to be and how unique Earth was. And that question got answered. Right. Which is pretty remarkable that in a lifetime you can have a 2,500-year-old question. The answer is they're everywhere. There are planets everywhere. And it was possible that planets were really rare. We didn't really understand how planets formed. And so if you go back to, say, the turn of the 20th century, there was a theory that said planets formed when two stars passed by each other closely, and then material was gravitationally squeezed out, in which case those kinds of collisions are so rare that you would expect 1 in a trillion stars to have planets. Instead, every star in the night sky has planets.
So one of the things you've done is simulated the formation of stars. How difficult do you think it is to simulate the formation of planets, like simulate a solar system through the entire evolution of the solar system? This is kind of a numerical simulation sneaking up to the question of how many planets are there.
That actually we're able to do now. You can run simulations of the formation of planetary system. So if you run the simulation, really where you want to start is a cloud of gas, these giant interstellar clouds of gas that may have 1,000,000 times the mass of the sun in them. And so you run a simulation of that. It's turbulent. The gas is roiling and tumbling. And every now and then you get a place where the gas is dense enough that gravity gets hold of it and it can pull it downward. So you'll start to form a protostar. And a protostar is basically the young star of this ball of gas where nuclear reactions are getting started. But it's also a disk. So as material falls inward, because everything's rotating, as it falls inward, it'll spin up and then it'll form a disk. Material will collect in what's called an accretion disk or a protoplanetary disk. And you can simulate all of that. Once you get into the disk itself and you want to do planets, things get a little bit more complicated because the physics gets more complicated. Now you got to start worrying about dust, because actually dust is the wrong word. It's smoke, really. These are the tiniest bits of solids. They will coagulate in the disk to form pebbles, right? And then the pebbles will collide to form rocks, and then the rocks will form boulders, et cetera, et cetera. That process is super complicated, but we've been able to simulate enough of it to begin to get a handle on how planets form, how you accrete enough material to get the first proto-planets or planetary embryos, as we call them. And then the next step is those things start slamming into each other to form, planetary-sized bodies. And then the planetary bodies slam into each other. Earth, the moon, came about because there was a Mars-sized body that slammed into the Earth and basically blew off all the material that then eventually formed the moon.
And all of them have different chemical compositions, different temperatures.
Yeah, so the temperature of the material in the disk depends on how far away you are from the star. So it decreases, right? And so there's a really interesting point. So close to the star, temperatures are really high. And the only thing that can condense, that can kind of freeze out, is going to be stuff like metals. So that's why you find Mercury is this giant ball of iron, basically. And then as you go further out, the gas gets cooler, and now you can start getting things like water to freeze, right? So there's something we call the snow line, which is somewhere in our solar system out around between Mars and Jupiter. And that's the reason why the giant planets in our solar system, Jupiter, Saturn, Uranus, and Neptune, all have huge amounts of ice in them, or water and ice. Actually, Jupiter and Saturn don't have so much, but the moons do. The moons have so much water in them that there's oceans, right? That we've got a number of those moons have got more water on them than there's water on Earth.
Do you think it's possible to do that kind of simulation to have a stronger and stronger estimate of how likely an Earth-like planet is? Can we get the physics simulation done well enough to where we can start estimating, like, what are the possible Earth-like things that could be generated?
Yeah, I think we can. I think we're learning how to do that now. So one part is like trying to just figure out how planets form themselves and doing the simulations, like that cascade from dust grains up to planetary embryos. That's hard to simulate because it's both. You got to do both the gas and you got to do the dust and the dust colliding and all that physics. Once you get up to a planet-sized body, then you kind of have to switch over to almost like a different kind of simulation. There, often what you're doing is you're assuming the planet is this sort of spherical ball, and then you're doing like a 1D, a radial calculation. And you're just asking like, all right, how is this thing what is the structure of it going to be? Like, am I going to have a solid iron core, or am I going to get a solid iron core with that liquid iron core out around it like we have on Earth? And then you get, a silicate, kind of a rocky mantle, and then a crust. All of those details, those are kind of beyond being able to do full 3D simulations from ab initio, from scratch. We're not there yet.
How important are those details, like the crust and the atmosphere, do you think?
Hugely important. So I'm part of a collaboration at the University of Rochester where we're using the giant laser. This is called the Laboratory for Laser Energetics. We got a huge grant from the NSF to use that laser to like slam tiny pieces of silica to understand what the conditions are like at the center of the Earth, or even more importantly, the center of super Earths. Like this is what's wild. The most common kind of planet in the universe we don't have in our solar system, which is amazing, right? So we've been able to study enough or observe enough planets now to get a census. We kind of have an idea of who's average, who's weird. And our solar system's weird because the average planet has a mass somewhere between a few times the mass of the Earth to maybe, 10 times the mass of the Earth. And that's exactly where there are no planets in our solar system. So the smaller ones of those we call super Earths. The larger ones we call sub-Neptunes. And they're anybody's guess. Like, we don't really know what happens to material when you're squeezed to those pressures, which is like millions, tens of millions of times the pressure on the surface of the Earth. So those details really will matter of what's going on in there, because that will determine whether or not you have, say, for example, plate tectonics. We think plate tectonics may have been really important for life on Earth, for the evolution of complex life on Earth. So it turns out, and this is sort of the next generation where we're going with the understanding the evolution of planets and life. It turns out that you actually have to think hard about the planetary context for life. You can't just be like, oh, there's a warm pond, and then some interesting, chemistry happens in the warm pond. You actually have to think about the planet as a whole and what it's gone through in order to really understand whether a planet is a good place for life or not.
Why do you think plate tectonics might be useful for the formation of complex life?
There's a bunch of different things. One is that, the Earth went through a couple of phases of being a snowball planet. Like we went into a period of glaciation where pretty much the entire planet was under ice. The oceans were frozen. Early on in Earth's history, there was barely any land. We were actually a water world, with just a couple of Australia-sized cratons, they called them, protocontinents. So those, we went through these snowball Earth phases. And if it wasn't for the fact that we had kind of an active plate tectonics, which had a lot of volcanism on it, we could have been locked in that forever. Like, once you get into a snowball state, a planet can be trapped there forever, which is, maybe you already had life form, but then because it's so cold, you may never get anything more than just microbes. Right. So what plate tectonics does is because it fosters more volcanism, is that you're going to get carbon dioxide pumped into the atmosphere, which warms the planet up and gets you out of the snowball Earth phase. But there's even more really important things. I just finished a paper where we were looking at something called the hard steps model, which is this model that's been out there for a long time that purports to say intelligent life in the universe will be really rare. And it made all these assumptions about the Earth's history, particularly that the history of life and the history of the planet have nothing to do with each other. And it turns out, as I was doing the reading for this, that Earth probably early on had a more mild form of plate tectonics, and then somewhere about 1 billion years ago, it ramped up. And that ramping up changed everything on the planet. Because here's a funny thing: the Earth used to be flat. What I mean by that, right? So all the flat earthers out there can get excited for 1 second.
Clip it.
What
Still is.
what I mean by that is that there really weren't many mountain ranges, right? The beginning of, I think the term is orogenesis, mountain building, the true Himalayan style giant mountains didn't happen until this more robust form of plate tectonics, where the plates are really being driven around the planet. And that is when you get the crusts hitting each other and they start pushing, into these Himalayan style mountains. The weathering of that, the erosion of that, puts huge amounts of nutrients, things that microbes want to use, into the oceans, and then what we call the net primary productivity, the bottom of the food chain, how much sugars they are producing, how much photosynthesis they're doing, shot up by a factor of almost 1,000. Right, so the fact that you had plate tectonics supercharged evolution in some sense. We're not exactly sure how it happened, but it's clear that the amount of life, the amount of living activity that was happening really got a boost from the fact that suddenly there was this new vigorous form of plate tectonics.
So it's nice to have turmoil in terms of temperature, in terms of surface geometries, in terms of the chemistry of the planet, turmoil.
Yeah, that's actually really true, because what happens is if you look at the history of life, that's it's an excellent point you're bringing up. If you look at the history of life on Earth, we get, abiogenesis somewhere around at least 3.8 billion years ago. And that's the first microbes. They kind of take over enough that they really do, you get a biosphere. You get a biosphere that is actively changing the planet. But then you go through this period they call the boring billion, where it's 1 billion years and it's just microbes. Nothing's happening. It's just microbes. I mean, the microbes are doing amazing things. They're inventing fermentation. Thank you very much we appreciate that. But it's not until sort of you get probably these continents slamming into each other, you really get the beginning of continents forming and driving changes that evolution has to respond to. That on a planetary scale, this turmoil, this chaos is creating new niches as well as closing other ones. And evolution has to respond to that. And somewhere around there is when you get the Cambrian explosion, is when suddenly every body plan, evolution goes on an orgy, essentially. So yeah, it does look like that chaos or that turmoil was actually very helpful to evolution.
I wonder if there's some extremely elevated levels of chaos, almost like catastrophes, behind every leap of evolution. Like you're not going to have leaps. Like in human societies, we have like an Einstein that comes up with a good idea, but it feels like on an evolutionary time scale, you need some real big drama going on for the evolutionary system to have to come up to a solution to that drama, like an extra complex solution to that drama.
Well, I think I'm not sure if that's true. I don't know if it needs to be like an almost extinction event, right? Because it's certainly true that we have gone through almost extinction events, right? We've had, 5 mass extinctions, but you don't necessarily see that like there was this giant evolutionary leap happening after those. So, with the comet impact, the KT boundary, certainly, lots of niches opened up. And that's why we're here, right? Because, our ancestors were just little, basically rodents, rats, living under the footsteps of the dinosaurs. And it was that comet impact that opened the route for us. But it wasn't, that still took another, 65 million years. It wasn't like this thing immediately happened. But what we found with this hard steps paper, because the whole idea of the hard steps paper was, it was one of these anthropic reasoning kinds of things where Brandon Carter said, oh, look, the intelligence doesn't show up on Earth until about, almost close to when the end of the sun's lifetime. And so he's like, well, there should be no reason why the sun's lifetime and the time for evolution to produce intelligence should be the same. And so therefore, and he goes through all this reasoning, anthropic reasoning, and he ends up with the idea that like, oh, it must be that the odds of getting intelligence are super low. And so that's the hard steps, right? So there was a series of steps in evolution that were, very, very hard. And because of that, you can calculate some probability distributions. And everybody loves a good probability distribution. And they went a long way with this. But it turns out that the whole thing is flawed because on one, when you look at it, of course, the time scale for the sun's evolution and the time scale for evolution on life are coupled because life and the time scale for evolution of the Earth is about the same timescale as the evolution as the sun. It's billions of years. The Earth evolves over billions of years. And life and the Earth co-evolve. That's what Brandon Carter didn't see, is that actually the fate of the Earth and the fate of life are inextricably combined. And this is really important for astrobiology, too. Life doesn't happen on a planet. It happens to a planet. So this is something that David Grinspoon and Sarah Walker both say. And, I agree with this. It's a really nice way of putting it. Plate tectonics, the evolution of oxygen, of an oxygen atmosphere, which only happened because of life. These things, these are things that are happening where life and the planet are sort of sloshing back and forth. Mm-hmm. And so rather than, to your point about, do you need giant catastrophes? Maybe not giant catastrophes, but what happens is, as the Earth and life are evolving together, windows are opening up, evolutionary windows. Like, for example, life put oxygen into the atmosphere. When life invented this new form of photosynthesis about 2.5 billion years ago, that broke water apart to, work to do its chemical shenanigans. It broke water apart and pushed oxygen into the atmosphere. That's why there's oxygen in the atmosphere. It's only because of life. That opened up huge possibilities, new spaces for evolution to happen. But it also changed the chemistry of the planet forever. So the introduction of oxygen photosynthesis changed the planet forever, and it opened up a bunch of windows for evolution that wouldn't have happened otherwise. Like, for example, you and I, we need that amount of oxygen. Big-brained creatures need an oxygen-rich atmosphere because oxygen is so potent for metabolism. So you couldn't get intelligent creatures 100 million years after the planet formed.
So really, on a scale of a planet, when there's billions, trillions of organisms on a planet, they can actually have planetary scale impact.
Yeah.
So the chemical shenanigans of an individual organism, when scaled out to trillions, can actually change a planet.
Yeah, and we know this for a fact now. Like, so there was this thing, Gaia theory, that with James Lovelock introduced in the 70s, and then Lynn Margulis, the biologist Lynn Margulis, together. So this Gaia theory was the idea that planets pretty much life takes over a planet. Life hijacks a planet in a way that the sum total of life creates these feedbacks between the planet and the life, such that it keeps the planet habitable. It's kind of a homeostasis, right? I can go out, like right now outside it's 100 degrees, right? And I go outside, but my internal temperature is going to be the same. And I can go back to, Rochester, New York in the winter, and it's going to be, 0 degrees, but my internal temperature is going to be the same. That's homeostasis. The idea of Gaia theory was that life, the biosphere, exerts this pressure on the planet, or these feedbacks on the planet, that even as other things are changing, the planet will always stay in the right kinds of conditions for life. Now, when this theory came out, it was very controversial. People were like, oh my God, what are you, smoking weed? And like, there were all these Gaian festivals with Gaian dances. And so, it became very popular in the New Age community. But Lovelock, actually, they were able to show that, no, this has nothing to do with like the planet being conscious or anything. It was about these feedbacks that by the biology, the biosphere can exert these feedbacks. And now that's become, whether or not we're still unclear whether there are true Gaian feedbacks in the sense that the planet can really exert complete control. But it is absolutely true that the biosphere is a major player in Earth's history.
So the biosphere fights for homeostasis on Earth.
What I would say right now is, I don't know if I can say that scientifically. I can certainly say that the biosphere does a huge amount of the regulation of the planetary state, and over billions of years has strongly modified the evolution of the planet. So whether or not a true Gaian feedback would be exactly what you said, right? The biosphere is this somehow, and Sarah Walker and David Grinspoon and I actually did a paper on this about the idea of planetary intelligence or cognition across a planetary scale. And I think that actually is possible. It's not conscious, but there is a kind of cognitive activity going on. The biosphere, in some sense, knows what is happening because of these feedbacks. So it's still unclear whether we have these full Gaian feedbacks, but we certainly have semi-Gaian feedbacks. If there's a perturbation on the planetary scale, temperature, insolation, how much sunlight's coming in, the biosphere will start to have feedbacks that will damp that perturbation. Temperature goes up, the biosphere starts doing something, temperature comes down.
Now, I wonder if the technosphere also has a Gaian feedback or elements of a Gaian feedback, such that the technosphere will also fight to some degree for homeostasis? Open question, I guess.
Well, I'm glad you asked that question, because that paper that David and Sarah and I wrote, what we were arguing is that over the history of a planet, right? When life first forms, 3.8 billion years ago, it's kind of thin on the ground, right? You've got the first species, these are all microbes, and they have not yet they're not going to, enough of them to exert any kind of these Gaian feedback. So we call that an immature biosphere.
Mm-hmm.
But then as time goes on, as life becomes more robust and it begins to exert these feedbacks, keeping the planet in the place where it needs to be for life, we call that a mature biosphere, right? And the important thing, and I'm sure later on, we're going to talk about definitions of life and such. There's this great term called autopoiesis that Francisco Varela, the neurobiologist Francisco Varela, came up with. And he said, one of the defining things about life is this property of autopoiesis, which means self-creating and self-maintaining. Life does not create the conditions which will destroy itself, right? It's always trying to keep itself in a place where it can stay alive. So the biosphere, from this Gaian perspective, has been autopoietic for billions of years. Now, we just invented this technosphere in the last couple of hundred years, and what we were arguing in that paper is that it's an immature technosphere, right? Because right now, with climate change and all the other things we're doing, the technosphere right now is sort of destroying the conditions under which it needs to maintain itself. So the real job for us, if we're going to last over geologic timescales, if we want a technosphere that's going to last tens of thousands, hundreds of thousands, millions of years, then we've got to become mature, which means to not undermine the conditions, to not subvert the conditions that you need to stay alive. So as of right now, I'd say we're not autopoietic.
Well, I wonder if we look across thousands, tens of thousands, hundreds of thousands of years, that the technosphere should create perturbations as a way for developing greater and greater defenses against perturbations, which sounds like a ridiculous statement, but basically go out and play in the yard and hurt yourself to strengthen or like drink water from the pond.
From the pond, yeah, right. Get sick a few times.
To strengthen the immune system.
Yeah. Well, what's interesting with the technosphere, we could talk about this more, but we're just emerging as a technosphere in terms of as a interplanetary technosphere, right? That's really the next step for us is to, David Grinspoon talks about, I love this idea of anti-accretion, like this amazing thing that for the first time, over the entire history of the planet, stuff is coming off the planet, right? It used to be everything just fell down, all the meteorites fell down. But now we're starting to push stuff out. And, like the idea of planetary defense or such, we are actually going to start exerting perturbations on the solar system as a whole. We're going to start engineering if we make it, right? I always like to say that if we can get through climate change, the prize at the end is the solar system, right? So we will be literally engineering the solar system. But what you can think of right now with what's happening with the Anthropocene, the great acceleration that is the technosphere, is the creation of it. That is a giant perturbation on the biosphere, right? And what you can't do is, the technosphere sits on top of the biosphere, and if the technosphere undermines the biosphere for its own conditions of habitability, then you're in trouble, right? I mean, the biosphere is not going away. There's nothing we could do. Like the idea that we have to save the Earth is a little ridiculous. Like the Earth is not a furry little bunny that we need to protect, but it's the conditions for us, right? Humanity emerged out of the Holocene, the last 10,000 years interglacial period. We can't tolerate very different kinds of Earths. So that's what I mean about a perturbation.
Before we forget, I got to ask you about this paper.
Right.
Pretty interesting. There's an interesting table here about hard steps. Yeah. Abiogenesis, glucose fermentation to pyruvic acid, all kinds of steps, all the way to Homo sapiens, animal intelligence, land ecosystems, endoskeletons. Eye precursor, so formation of the eye.
Yeah.
Complex multicellularity.
That's definitely one of the big ones.
Yeah, so interesting. I mean, what can you say about this chart? There are all kinds of papers talking about what the difficulty of these steps.
Right. And so this was the idea. So what Carter said was, using anthropic reasoning, he said there must be a few very hard steps for the evolution to get through to make it to intelligence. Right. So there's some steps are going to be easy. So every generation, you roll the dice and it won't take long for you to get that step. But there must be a few of them. And he said you could even calculate how many there were, 5, 6, in order to get to intelligence. And so this paper here, this plot, is all these different people who've written all these papers. And this is the point, actually. You can see all these papers that were written on the hard steps, each one proposing a different set of what those steps should be. And there's this other idea from biology of the major transitions in evolution, MTEs, that those were the hard steps. But what we actually found was that none of those are actually hard. The whole idea of hard steps, that there are hard steps, is actually suspect. So, what's amazing about this model is it shows how important it is to actually work with people who are in the field, right? Mm-hmm. So, Brandon Carter was a brilliant physicist, the guy who came up with this. And then lots of physicists and astrophysicists like me have used this, but the people who actually study evolution and the planet were never involved, right? And if you went and talked to an evolutionary biologist or a biogeophysicist, they'd look at you when you explained this to them and they'd be like, what? Like, what are you guys doing? Turns out none of the details or none of the conceptual structure of this matches with what the people actually study the planet and its evolution.
Is it mostly about the fact that there's not really discrete big steps? It's a gradual, continual kind of process?
Well, there's two things. The first most important one was that the planet and the biosphere have evolved together. That's something that most biogeophysicists completely accept. And it was the first thing that Carter kind of rejected. He said, no, that's probably not possible. And yet, if he'd only sort of had more discussions with this other community, would have seen no, there are actually windows that open up. And then the next thing is this idea of whether a step is hard or not. Because for hard, what you mean by a hard step is that, like I said, every time there's a generation, every time there's the next generation born, you're rolling the dice on whether this mutation will happen. And the idea of something being a hard step, there's two ways in which something might even appear as a hard step and not be, or actually not be a hard step at all. One is that you see something that has occurred in evolution and it's only happened once, right? So let's take the opposite. You see something that's happened multiple times, like wings. Lots of examples of wings over lots of different evolutionary lineages. So that's clearly not a hard. Making wings is not a hard step. There are certain other things that people say, no, that's a hard step. Oxygen, the oxygen photosynthesis. But they tend to be so long ago that we've lost all the information. There could be other things in the fossil record that, made this innovation, but they're just gone now. So you can't tell. So there's information loss. The other thing is the idea of pulling up the ladder, that somebody, some species makes the innovation, but then it fills the niche and nobody else can do it again. So yeah, it only happened once, but it happened once because basically the creature was so successful, it took over and there was no space for anybody else to evolve it. So yeah, so the interesting thing about this was seeing how much, once you look at the details of life's history on Earth, how it really shifts you away from this hard steps model. And it shows you that those details, as we were talking about, do you have to know about the planet? Do you have to know about plate tectonics? Yeah, you're going to have to.
I mean, to be fair to Carter on the first point, it makes it much more complicated if life and the planet are co-evolving. Because it would be nice to consider the planet as a static thing that sets the initial conditions.
Yeah.
And then we can sort of, from an outside perspective, analyze planets based on the initial conditions they create. And then there's a binary yes or no, will it create life? But if they co-evolve, it's just it's a really complex dynamical system where everything is becomes much more difficult from the perspective of SETI, of looking out there and trying to figure out which ones are actually producing life.
But I think we're at the point now, so now there may be other kinds of principles that actually, because, coevolution actually has its own, not deterministic, you're done with determinism, right? Yep. But complex systems have patterns. Complex systems have constraints. And that's actually what we're going to be looking for, are constraints on them. And so, and again, nothing against Carter. It was a brilliant idea, but it just goes to show, there's this great XTC. I'm a theoretical physicist, right? So I love give me a simplified model with, it's a dynamical equation, some initial conditions. I'm very happy. But there's this great XTC comic where somebody's working something out on the board and this physicist is looking over and saying, I just wrote down an equation for that. I solved your problem. Do you guys even have a journal for this? And the subtitle is why everybody hates physicists.
Yeah.
So sometimes that approach totally works.
Yeah.
Sometimes physicists, we can be very good at like zooming in on what is important and casting the details aside so you can get to the heart of an issue. And that's very useful sometimes. Other times it obfuscates, right? Other times it clouds over actually what you needed to focus on, especially when it comes to complexity.
Speaking of simplifying everything down to an equation, let's return back to the question of how many alien civilizations are out there and talk about the Drake equation.
Yeah.
Can you explain the Drake equation?
People have various feelings about the Drake equation. It can be abused, but basically it was the story actually is really interesting. So Frank Drake in 1960 does the first ever astrobiological experiment. He gets a radio telescope, points it at a couple of stars, and listens for signals. That was the first time anybody done any experiment about any kind of life in the history of humanity. And he does it, and he's kind of waiting for everybody to make fun of him. Instead, he gets a phone call from the government, says, "Hey, we want you to do a meeting on interstellar communications," right? So he's like, okay. So they organize a meeting with like just 8 people. A young Carl Sagan is going to be there as well. And like the night before, Drake has to come up with an agenda. How do you come up with an agenda for a meeting on a topic that no one's ever talked about before, right? And so he breaks what he does. What's so brilliant about the Drake equation is he breaks the problem of how many civilizations are there out there into a bunch of sub-problems, right? And he breaks it into 7 sub-problems. Each one of them is a factor in an equation that when you multiply them all together, you get the number of civilizations out there that we could communicate with. So the first term is the rate at which stars form. The second term is the fraction of those stars that have planets, F sub p. The next term is the number of planets in the habitable zone, the place where we think life could form. The next term after that is the fraction of those planets where actually an abiogenesis event, life forms, occurs. The next one is the fraction of planets on which you start to get intelligence. After that, it's the fraction of planets where that intelligence goes on to create a civilization. And then finally, the last term, which is the one that we really care about, is the lifetime. How long you have a civilization, now how long does it last?
Well, you say we humans.
We humans, right? Because we're staring at the multiple guns pointing at us. Nuclear war, climate change, AI. So how long in general does civilizations last? Now, each one of these terms, what was brilliant about what he did was he was quantifying our ignorance, right? By breaking the problem up into these 7 sub-problems, he gave astronomers something to do. Right. And so, this is always with a new research field. You need a research program, or else you just have a bunch of vague questions. You don't even know really what you're trying to do. So, the star people could figure out how many stars were forming per year. The people who were interested in planets could go out and find techniques to discover planets, et cetera, et cetera.
I mean, these are their own fields. Essentially, by creating this equation, he's launching new fields.
Yeah, that's exactly. He gave astrobiology, which wasn't even a term then, a roadmap. Like, okay, you guys go do this, you go do that, you go do that. And it had such far-reaching effect on astrobiology because it did break the problem up in a way that gave useful, sort of marching orders for all these different groups. Like, for example, it's because of the Drake equation in some sense that people who were involved in SETI pushed NASA to develop the technologies for planet hunting. There was this amazing meeting in 1978, 1978 and 1979, that were driven in some part by the people who were involved in SETI getting NASA together to say, look, how, what's the roadmap for us to develop technologies to find planets? So, the Drake equation is absolutely foundational for astrobiology, but we should remember that it's not a law of nature, right? It's not something it's not E equals MC squared. And so you can see it being abused in some sense. People, it's generated 1 trillion papers. Some of those papers are good. I've written some of those, and some of those papers are bad. I'm not sure where my paper fits in on those. I'm just saying, one should be careful about what you're using it for. But in terms of understanding the problem that astrobiology faces, this really broke it up in a useful way.
We could talk about each one of these, but let's just look at exoplanets.
Yeah.
So that's a really interesting one. I think when you look back, hundreds of years from now, what is it, in the 90s when they first detected
90,
the
yeah,
first?
92 and 95. 95 to me was really, that was the discovery of the first planet orbiting a sun-like star. To me, that was the dam being broken.
I think that's like one of the greatest discoveries in the history of science.
I agree. I agree.
Right now, I guess nobody's celebrating it too much because you don't know what it really means. But I think once we almost certainly will find life out there, it will obviously allow us to generalize across the entire galaxy, the entire universe. So if you can find life on a planet, even in the solar system, you can now start generalizing across the entire universe.
You can. All you need is one. Like right now, it's an any. Our understanding of life. We have one example. We have n equals one example of life. So that means we could be an accident, right? It could be that we're the only place in the entire universe where this weird thing called life has occurred. Get one more example, and now you're done. Because if you have one more example, now you don't have to find all the other examples. You just know that it's happened more than once, and now you are, from a Bayesian perspective, you can start thinking like, this life is not something that's hard to make.
Well, let me get your sense of estimates for the Drake equation. You've also written a paper expanding on the Drake equation, but what do you think is the answer?
So there was this paper we wrote, Woody Sullivan and I, in 2016, where we said, look, we have all this exoplanet data now, right? So the thing that exoplanet science and the exoplanet census I was talking about before have nailed is F sub p, the fraction of stars that have planets, it's 1. Every frickin' star that you see in the sky hosts a family of worlds. I mean, it's mind-boggling because every one of those are all places, right? They're either gas giants, probably with moons. So the moons are places you can stand and look out. Or they're like terrestrial worlds where even if there's not life, there's still snow falling and there's oceans washing up on shorelines. It's incredible to think how many places and stories there are out there. So, right, the first term was F sub p, which is how many stars have planets. The next term is how many planets are in the habitable zone, right, on average. And it turns out to be 1/5. Right. So, around 0.2. So that means you just count 5 of them, go out at night and go 1, 2, 3, 4, 5. One of them has an Earth-like planet, in the habitable zone. Like, whoa.
So what defines a habitable zone?
Habitable zone is an idea that was developed in the 1958 by the Chinese-American astronomer Xu Sheng. And it was a brilliant idea. It said, look, this is I can do this simple calculation. If I take a planet and just stick it at some distance from a star of what's the temperature of the planet? What's the temperature of the surface? So now you're going to ask, you give it a standard kind of, Earth-like atmosphere and ask, could there be liquid water on the surface, right? We believe that liquid water is really important for life. There could be other things that's happening, fine. But, if you were to start off trying to make life, you'd probably choose water as your solvent for it. So basically, the habitable zone is the band of orbits around a star where you can have liquid water on the surface. You could take a glass of water, pour it on the surface, and it would just pool up. It wouldn't freeze immediately, which would happen if your planet is too far out, and it wouldn't just boil away if your planet's too close in. So that's the formal definition of the habitable zone. So it's a nice, strict definition. There's probably way more going on than that, but this is a place to start.
Right. Well, we should say it's a place to start. I do think it's too strict of a constraint.
I would agree.
We're talking about temperature where water can be on the surface. There's so many other ways to get the aforementioned turmoil, where the temperature varies, whether it's volcanic, so interaction of volcanoes and ice and all of this on the moons of planets that are much farther away, all this kind of stuff.
Yeah. Well, for example, we know in our own solar system, we have, say, Europa, the moon of Jupiter, which has got 100-mile deep ocean under 10 miles of ice, right? That's not in the habitable zone. That is outside the habitable zone. And that may be the best place. It's got more water than Earth does. All of its oceans are, it's twice as much water on Europa than there is on Earth. So, that may be a really great place for life to form, and it's outside the habitable zone. So, the habitable zone is a good place to start, and it helps us. And there's reasons why you do want to focus on the habitable zone, because like Europa, I won't be able to see from across telescopic distances, across light years. I wouldn't be able to see life on Europa because it's under 10 miles of ice, right? So with the important thing about planets in the habitable zone is that we're thinking they have atmospheres. Atmospheres are the things we can characterize for across 10, 50 light years, and we can see biosignatures, as we're going to talk about. So there is a reason why the habitable zone becomes important for the detection of extrasolar life.
But for me, when I look up at the stars, it's very likely that there's a habitable planet or moon in each of the stars. Habitable defined broadly.
Yeah, I think that's not unreasonable to say. I mean, especially since the formal definition, you get 1 in 5, right? 1 in 5 is a lot. There's a lot of stars in the sky. So yeah, saying that in general, when I look at a star, there's a pretty good chance that there's something habitable orbiting it is not a unreasonable scientific claim.
To me, it seems like there should be alien civilizations everywhere. Why the Fermi paradox? Why haven't we seen them?
Okay, the Fermi paradox. Let's talk about I love talking about the Fermi paradox because there is no Fermi paradox. Dun, 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 dun. Yeah, so the Fermi paradox, let's talk a little about the Fermi paradox and the history of it. Enrico Fermi, it's 1950. He's walking with his friends at Los Alamos Nuclear Weapons Lab to the cantina, and there had been this cartoon in the New Yorker. They all read the New Yorker. And the cartoon was trying to explain why there'd been this rash of garbage cans disappearing in New York. And this cartoon said, oh, it's UFOs. Because this is already, it's 1950. The first big UFO craze happened in 47. So they were laughing about this as they're walking, and they started being physicists, started talking about interstellar travel, interstellar propulsion, blah, blah, blah. Conversation goes on for a while. Conversation turns to something else, they've gone to other things. About 40 minutes later, over lunch, Fermi blurts out, well, where is everybody? Right? Typical Fermi sort of thing. He'd done the calculation in his head, and he suddenly realized that, look, if intelligence is common, that even traveling at sublight speeds, a civilization could cross, kind of hop from one star system to the other and spread out across the entire galaxy in a few 100,000 years. And he realized this, and so he was like, why aren't they here now? And that was the beginning of the Fermi paradox. It actually got picked up as a formal thing in 1975 in a paper by Hart, where he actually kind of went through this calculation and showed and said, well, there's nobody here now, therefore there's nobody anywhere. Okay, so that is what we will call the direct Fermi paradox. Why aren't they here now? But something happened where people, after SETI began, where people started to, there was this idea of the great silence. People got this idea in their head that like, oh, we've been looking for decades now for signals of extraterrestrial intelligence, and we haven't found any. Therefore, there's nothing out there. So we'll call that the indirect Fermi paradox. And there absolutely is no indirect Fermi paradox for the most mundane of reasons, which is money. There's never been any money to look. SETI was always done by researchers who were kind of like scabbing some time, some extra time from their other projects to, look a little bit at the sky with a telescope. Telescopes are expensive. So Jason Wright, one of my collaborators, he and his students did a study where they looked at the entire search space for SETI. And imagine that's an ocean. All the different stars you have to look at, the radio frequencies you have to look at, when you look, how often you look. And they looked, then they summed up all the SETI searches that had ever been done. They went through the literature. And what they found was if that search space, if the sky is an ocean and you're looking for fish, how much of the ocean have we looked at? And it turns out to be a hot tub. That's how much of the ocean that we've looked up. We've dragged a hot tub's worth of ocean water up, and there was no fish in it. And so now are we going to say, oh, well, there's no fish in the ocean, right? So there is absolutely, positively no indirect Fermi paradox. We just haven't looked. But we're starting to look. So that's what's, finally we're starting to look. That's what's exciting. The direct Fermi paradox, there are so many ways out of that, right? There's a book called 77 Solutions to the Fermi Paradox that it just, you can pick your favorite one. It just doesn't carry a lot of weight because there's so many ways around it. We did an actual simulation, my group, Jonathan Carroll, one of my collaborators, we actually simulated the galaxy, and we simulated probes moving at sublight speed from one star to the other, gathering resources, heading to the next one. And so we could actually track the expansion wave across the galaxy, have one abiogenesis event, and then watch the whole galaxy get colonized or settled. And it is absolutely true that wave crosses, Hart was right, Fermi was right, that wave crosses very quickly. But civilizations don't last forever, right? So one question is, when did they visit? When did they come to Earth, right? So if you give civilizations a finite lifetime, let them last 10,000, 100,000 years, what you find is you now have a steady state. Civilizations are dying, they're coming back, they're traveling between the stars. What you find then is you can have big holes opened up. You can have regions of space where there is nobody for, millions of years. And so if we're living in one of those bubbles right now, then maybe we were visited, but we were visited 100 million years ago. And there was a paper that Gavin Schmidt and I did that showed that if there was a civilization, whether it was like dinosaurs or aliens that was here 100 million years ago, there's no way to tell. There's no record left over. The fossil record is too sparse. The only way maybe you could tell is by looking at the isotopic strata to see if there was anything reminiscent of an industrial civilization. But the idea that, you'd be able to find iPhones or toppled buildings after 100 million years there's no way.
So if there was an alien camp here,
yeah,
an alien village, a small civilization,
right.
Maybe even a large civilization,
even a large civilization, even if it was
100 million years ago,
and it lasted 10,000 years, fossil record's not going to have it. Yeah. The fossil record is too sparse, right? Most things don't fossilize.
Yeah.
And 10,000 years is a blink in the eye of geological time. So Gavin called this the Silurian hypothesis after the Doctor Who episode with the lizard creatures, the Silurians. And so that paper got a lot of press, but it was it was an important idea. And it was really Gavin's. I was just helping with the astrobiology, that to recognize that, we could have been visited a long time ago. There just would be no record. Yeah, it's kind of mind-blowing.
It's really mind-blowing.
Yeah.
And it's also a good reminder that we've been intelligent species have been here for a very short amount of time.
Very short amount of time, yeah. This is not to say that there was, whenever I gave, I was on Joe Rogan for exactly this paper, and I had to always emphasize, we're not saying there was a Silurian, but we're just saying that if there was. That's why I loved Gavin's question. Gavin's question was just how could you tell? Right? It was a very beautifully scientific question. That's what we were really showing, is that you really, unless you did a very specific kind of search, which nobody's done so far, that, there's not an obvious way to tell that there could have been civilizations here earlier on.
I've actually been reading a lot about ancient civilizations, and it just makes me sad how much of the wisdom of that time is lost.
Yeah.
And how much guessing is going on. Whether it's in South America, what happened in the jungle.
Yeah, like the Amazon, the Amazon problem. That was, the conquistadors came and wiped everybody out, and especially just even the plague may have decimated. So yeah, how much of that civilization?
And there's a lot of theories, and because of archaeology only looks at cities, they don't really know the origins of humans.
Yeah.
And there's a lot of really interesting theories, and they're of course controversial. And there's a lot of controversial people in every discipline, but archaeology is it's a fascinating one because we know so little. They're basically storytellers. You're assembling the picture from just very few puzzle pieces. It's fascinating. It makes me it's humbling, and it's sad that there could be entire civilizations, ancient civilizations, that are either almost entirely or entirely lost.
Yeah, well, like the indigenous peoples of North America, there could have been millions and millions. We get this idea that the Europeans came and it was empty, but it may have only been empty because the plague had swept up from the what happened in Mesoamerica. So and they didn't really build cities, but they didn't build wooden or stone cities. They built wooden cities,
Everybody seems to be building pyramids, and they're really damn good at it. I don't know
what is up with a pyramid. Why does that apply? What archetype in our brain is that?
And it is also really interesting, speaking of archetypes, is that independent civilizations formed, and they had a lot of similar kind of dynamics, like human nature, when it builds up hierarchies in a certain way, builds up myths and religions in a certain way, it builds pyramids in a certain way.
Yeah.
It goes to war, all this kind of stuff.
Yeah.
Independently emerges. Fascinating.
Santa Fe Institute, the stuff the Santa Fe Institute does on this as complex systems, the origin of hierarchies and such, very cool.
Yeah, Santa Fe folks. Complexity in general is really
cool.
What phenomena emerge when a bunch of small things get together and interact. Going back to this paper, A New Empirical Constraint on the Prevalence of Technological Species in the Universe, this paper that expands on the Drake equation. What are some interesting things in this paper?
Well, so the main thing we were trying to do with this paper is say, look, we have all of this exoplanet data, right? It's got to be good for something, especially since two of the terms that have been nailed down empirically are two terms in the Drake equation. So F sub P, that's the second term, fraction of stars that have planets, and then N sub E, the average number of planets in the habitable zone. Those are the second and third term in the Drake equation. So what that means is all the astronomical terms have been nailed. And so we said, like, okay, how do we use this to do something with the Drake equation? And so what we realized is, well, okay, we got to get rid of time. The lifetime thing, we can't say anything about that. But if we if we don't ask how long do they last, but instead ask, what's the probability that there have been any civilizations at all, no matter how long they lasted? I'm not asking whether they exist now or not. I'm just asking in general about probabilities to make a technological civilization anywhere and at any time in the history of the universe. And that we were able to constrain. And so what we found was basically that there have been 10 billion trillion habitable zone planets in the universe. And what that means is those are 10 billion trillion experiments that have been run. And the only way that we're the only time that this is, this whole process from, abiogenesis to a civilization has occurred is if every one of those experiments failed, right? So therefore you could put a probability, we called it the pessimism line, right? We don't really know what nature sets for the probability of making intelligent civilizations, right? But we could set a limit using this. We could say, look, as if the probability per habitable zone planet is less than 10 to the minus 22, 1 in 10 billion trillion, then yeah, we're alone. If it's anywhere larger than that, then we're not the first. It's happened somewhere else. And to me, that was mind blowing. It doesn't tell me there's anybody nearby. The galaxy could be sterile. It just told me that, unless nature's really has some bias against civilizations, we're not the first time this has happened. This has happened elsewhere over the course of cosmic history.
10 billion trillion experiments.
Yeah, that's a lot of experiments.
That's a lot.
Right.
1,000 is a lot.
Yeah.
100 is a lot.
Yeah.
If we normal humans saw 100 experiments and we knew that at least one time there was a successful human civilization built, I mean, we would say for sure in 100 you'll get another one.
Yeah. Yeah. So that's what I mean. That's why. So this, these kinds of arguments, you have to be careful of what they can do. But I felt like what this paper showed was that, the burden of proof is now on the pessimists, right? So that's why we called it the pessimism line. There's been, throughout history, there's been, alien pessimists and alien optimists, and they've been yelling at each other. That's all they had to go with, right? And like with Giordano Bruno in 1600, they burned the guy at the stake for being an alien optimist. But nobody really knew what pessimism or optimism meant. This, we sort of thought this was like the Planck length. This was sort of the Planck length of astrobiology. Gave you an actual number that, if you could somehow calculate what the probability, of forming a technological civilization was, this thing sort of shows you where the limit is. As long as you're above 10 to the minus 22, then you absolutely, it has occurred in the history. Other civilizations have occurred in the history of the universe.
So to me, at least, the big question is FE, which is basically abiogenesis. How hard is it for life to originate on a planet? Because all the other ones seem very likely. Everything seems very likely. The only open question to me is like, how hard is it for life to originate?
There's lots of ways to, again, we don't know unless we look. And, you had Sarah Walker on not too long ago. She's very interested in origins of life. So, lots of people are working on this. But I think it's hard looking at the history of the Earth. And again, you can do Bayesian arguments on this. But yeah, forming life, I don't think it's hard. Getting like basic biology started, I don't think is hard. It's still wild. It's an amazing process that actually I think requires some deep rethinking about how we conceptualize what life is and what life isn't. That's one of the things I like about Sarah's work. We're pursuing on a different level about the life as the only process or the only system that uses information. But still, regardless of all those kinds of details, life is probably easy to make. That's my gut feeling.
Yeah, I mean, day by day this changes for me, but I just see that once you create bacteria, it's off to the races.
Yeah.
You're gonna get complex life.
Yeah.
As long as you have enough time. I mean, that boring billion but I just can't imagine a habitable planet not having a couple of billion to spare
Yeah, a
of
couple billion
years.
years to spare. There is a mystery there about why did it take so long, like with the Cambrian
Right.
explosion, but that may be again about these windows that like you couldn't happen until the planet and the life had evolved together enough that they together kind of opened the window for the next step. Um, you know, intelligent life and how long technological civilizations. I think there's a big question about how long those last and how I'm hopeful. Um, but in terms of just like, I think life is absolutely going to be common pretty common in the universe.
Yeah, I think it's absolutely like I think again, if I were to bet everything, even in advanced civilizations are common. So to me then the only explanation is the L. Our galaxy is a graveyard of civilizations.
Yeah, because you think about it, we've only been around. I mean, as a technological, truly, when we think about in Drake's definition, you had to have radio telescopes. That's been 100 years, And if we got another 10,000, 100,000 years of history, that for us, it'd be pretty amazing, right? But that wouldn't be long enough to really pop up the number of civilizations in the galaxy. So you really need it to be like hundreds of millions of years, and that raises a question which I am very interested in, which is how do you even talk about, I call it the billion-year civilization, right? How do we even begin to hypothesize or think about in any kind of systematic way what happens to a technological civilization across hundreds of millions to a billion years?
Yeah, like how do you even simulate the trajectories that civilizations can take across that kind of time scale?
Yeah.
When all the data we have is just for the 10,000 years or so, 20,000 years that humans have been building civilizations.
Yeah.
And then just I don't know what you put it at, but maybe 100 years that we've been
Yeah.
technological.
Yeah. And we're ready to blow ourselves to bits or, drive ourselves off the planet. Yeah, no, it's really interesting. But there's got to be a way. I think that's really a frontier. So you had David Kipping on not too long ago. And David and I did a paper, and Caleb Scharf, David really drove this, where it was a Bayesian calculation to sort of ask the question, if you were to find a detection, if you were to find a signal or, a techno signature, would that come from a civilization that was younger, your age, or older? And you could see, I mean, this is not hard to do, but it was great. The formalism was hard. It's kind of intuitive, but the formalism was hard to show that, yeah, they're older, probably much older. So that means you really do need to think about like, okay, how do billion-year civilizations manifest themselves? What signatures will they leave? And yeah, what's so cool about it? It's so much fun because you have to imagine the unimaginable. Like, would you still, obviously biological evolution can happen on those kinds of timescales. So you wouldn't even really be the same thing you started out as, but social forms, what kind of social forms can you imagine that would be continuous over that? Or maybe they wouldn't be continuous. They drop out, they destroy themselves and then they come back. So maybe it's a trunk or a punctuated evolution. But we got to this is the fun part. We have to sort of work this out.
Well, one way to approach that question is like, what are the different ways to achieve homeostasis as you get greater and greater technological innovation? So like if you expand out into the universe and you have up to Kardashev scale, what are the ways you can avoid destroying yourself? Just achieve stability while still growing.
Yeah.
And that's an interesting question. I think it's probably simulatable.
Could be. Agent-based modeling, you could do it with. That's so, our group has used agent-based modeling to do something like the Fermi paradox. That was agent-based modeling. But you can also do this. People at Santa Fe have done this. Other groups have done this use agent-based modeling to track the formation of hierarchies, the formation of stable hierarchies. So I think it's actually very doable. But understanding the kind of assumptions and principles that are going into it and what you can extract from those, that is what is sort of the frontier.
Do you think if humans colonize Mars, the dynamic between the civilization on Earth and Mars will be fundamentally different than the dynamic between individual nations on Earth right now? Like that's a thing to load into the agent-based simulation we're talking about.
If we settle it, Mars will very quickly want to become its own nation.
Well, no, there's already going to be nations on Mars. That's guaranteed.
Yeah,
the moment you have 2 million people, the moment you have 1 million people, there's going to be two tribes.
Right.
and then they're going to start fighting.
Right.
And the question is interplanetary fighting. How quickly does that happen? And does it have a different nature to it because of the distances, you know?
Are you a fan of The Expanse? Have you watched The Expanse? Great show. Because it's all about I highly recommend to everybody. It's based on a series of books that are excellent. It's on Prime, 6 seasons. And it's basically about the settled solar system. It takes place about 300 years from now. And the entire solar system is settled. And it is the best show about interplanetary politics. The first season, actually, the journal, what was it? Foreign Affairs said the best show on TV about politics. It takes place is interplanetary. So yeah, I think, human beings being human beings, yes, there will be warfare and there will be conflict. And I don't think it'll be necessarily all that different, because really, I think within a few hundred years, we will have lots of people in the solar system. And it doesn't even have to be on Mars. We did a paper where we looked based on, because I wanted to know about whether an idea in The Expanse was really possible. In The Expanse, the asteroid belt, what they've done is they have colonized the asteroid belt by hollowing out the asteroids and spinning them up and living on the inside, right? Because they have the Coriolis force. And I thought, like, wow, what a cool idea. And when I ran the blog for NPR, I actually talked to the guys and said, did you guys calculate this, see whether it's possible? Sadly, it's not possible. The rock is just not strong enough that if you tried to spin it up to the speeds you need to get 1/3 gravity, which is what I think the minimum you need for human beings, the rock would just fall apart. It would break. But we came up with another idea, which was that if you could take small asteroids, put a giant bag around them, a nanofiber bag, and spin those up, it would inflate the bag. And then even a small couple of kilometer wide asteroid would expand out to you could get like a Manhattan's worth of material inside. So forget about even colonizing Mars, space stations, right? Or space habitats with millions of people in them. So anyway, the point is that I think, within a few hundred years, it is not unimaginable that there will be millions, if not billions of people living in the solar system.
And so you think most of them will be in space habitats versus on Mars on the planetary surface?
It's a lot easier on some level, right? It depends on like with nanofabrication and such. But getting down a gravity well is hard, right? So there's a certain way in which there's a lot of it's a lot easier to build real estate out of the asteroids. But we'll probably do both. I mean, I think what'll happen is the next, should we make it through climate change and nuclear war and all the other and AI, the next 1,000 years of human history is the solar system, right? And so, I think we'll settle every nook and cranny we possibly can. And it's, it's a beautiful, what I love about what's hopeful about it is this idea you're going to have all of these pockets. And, I'm sure there's going to be a Mormon space habitat, there's going to be whatever you want, a libertarian space habitat. Everybody's going to be able to kind of create there'll be lots of experiments in human flourishing. And those kinds of experiments will be really useful for us to sort of figure out better ways for us to interact and have maximum flourishing, maximum wellness, maximum democracy, maximum freedom.
Do you think that's a good backup solution to go out into space, sort of to avoid the possibility of humans destroying themselves completely here on Earth?
Well, I think, I want to be always careful with that because, like I said, it's centuries that we're talking about,
yes.
Right? So, the problem with climate change, and same with nuclear war, it's breathing down our necks now. So it's not trying to establish a base on Mars is going to be so hard that it is not even going to be close to being self-sufficient for a couple of, a century at least. So it's not like a backup plan now. We have to solve the problem of climate change. We have to deal with that. There's still enough nuclear weapons to really do horrific things to the planet for human beings. So I don't think it's like a backup plan in that way, but I do think, like I said, it's the prize. It's, if we get through this, then we get the entire solar system to sort of play around in and experiment with and do really cool things with.
Well, I think it could be a lot less than a couple of centuries if there's a urgency, like a real urgency, like a catastrophe, like maybe a small nuclear war breaks out where it's like, holy shit, this is for sure a bigger one is looming.
Yeah.
Maybe if geopolitically the war between China and the United States escalates, where there's this tension that builds and builds and builds, and it becomes more obvious that we need to really, really, really accelerate.
Yeah. I think my only dilemma with that is that I just think that a self-sufficient base is so far away that, like, say you start doing that, and then there is a full-scale nuclear exchange. That base is, it's not going to last because it's just, the self-sufficiency requires a kind of an economy, like literally a material economy that we are so far from with Mars, that we are centuries from. Like I said, 3 centuries, which is not that long, 2 to 3 centuries. Look at 1820. Nobody had traveled faster than 60 miles an hour unless they were falling off a cliff, right? And now we routinely travel at 500 miles an hour. But it is sort of centuries long. So that's why I think we'd be better off trying to solve these problems than, I just think the odds that we're going to be able to create a self-sufficient colony on Mars before that threat comes to head is small. So we'd have to deal with the threat.
Yeah, it's an interesting scientific and engineering question of how to create a self-sufficient colony on Mars or out in space as a space habitat, like where Earth entirely could be destroyed, you could still survive.
Yeah. Because it's really what about, thinking about complex systems, right? A space habitat, would have to be as robust as an ecosystem, as the kind of thing, you go out and you see a pond with all the different webs of interactions. That's why I always think that, if this process of going out into space is actually will help us with climate change and with thinking about making a long-term sustainable version of human civilization. Because you really have to think about these webs, the complexity of these webs, and recognize the biosphere has been doing this forever. The biosphere knows how to do this, right? And so, how do we build a vibrant, powerful technosphere that also doesn't, mess with the biosphere's capacity to support our technosphere. So, by doing this, by trying to build space habitats, in some sense, you're thinking about building a small scale version of this. So I think the two problems are going to kind of feed back on each other.
Well, there's also the other possibility of like the movie Darren Aronofsky's Postcard from Earth, where we can create this kind of life gun that just shoots. So as opposed to engineering everything.
Yeah.
Basically seeding life on a bunch of places and letting life do its thing, which is really good at doing, it seems like. So as opposed to with a space habitat, you basically have to build the entire biosphere and technosphere, the whole thing by yourself.
Yeah.
If you just, hey, the aforementioned cockroach with some bacteria, place it in Europa, I think you'd be surprised what happens.
Yeah.
Right?
Yeah.
Like, honestly, if you put a huge amount of bacteria, like a giant number of organisms from Earth into on Mars, on some of these moons of the other planets in the solar system, do you think, I feel like some of them would actually find a way to survive?
The moon is hard because the moon is just like, there's no, the moon may be really hard. But, I wonder, somebody must have done these experiments, right? Like how, because we know there are extremophiles, right? We know that you can go down, 10 miles below the Earth's surface, and there are things where there's no sunlight. There's, the conditions are so extreme, and there's lots of microbes having a great time living off the radioactivity, in the rocks. But, they had lots of time to evolve to those conditions. So I'm not sure if you dumped a bunch of bacteria, so somebody must have done these experiments. How fast could microbial evolution occur under harsh conditions that you maybe get somebody who figures out, okay, I can deal with this. I think the moon's too much because it's so sterile. But, Mars, I don't know, maybe. I don't know. We'd have to, but it's an interesting idea.
I wonder if somebody has done those experiments.
Yeah, you think somebody would. Let's take a bunch of microbes.
Take the harshest possible condition of all different kinds, temperature, all this kind of stuff.
Right, pressure, salinity, and then just dump a bunch of things that are not used to it, and then just see, does everybody just die? That's it. There's,
The thing about life, it flourishes in a non-sterile environment where there's a bunch of options for resources, even if the condition is super harsh. In the lab, I don't know if you can reconstruct harsh conditions plus options for survival. You know what I mean? Like you have to have the huge variety of resources that are always available on a planet somehow, even when it's in super harsh conditions. So that's actually not a trivial experiment. And I wouldn't even, if somebody did that experiment in the lab, I'd be a little bit skeptical. Because I could see bacteria doesn't survive in this kinds of temperature. But then I'd be like, I don't know. Is there enough, right? Are there other options? Is the condition rich enough? Rich enough, yeah.
There's an alternative view though, which is there's this great book by Kim Stanley Robinson called Aurora. You know, so there's been a million century ship stories, like where, you know, Earth sends out a, you know, generation ship or century ship, and it goes to another planet, and they land and they colonize. And on this one, they get all the way there, and they think the planet's going to be habitable. And it turns out that it's not habitable for Earth life. Like that, you know, there's like, you know, bacteria or prions, actually, you know, that just like, you know, kill people in the simplest way. And the important thing about this book was the idea that, like, you know, life is actually very tied to its planet. Mm-hmm. It may not be so easy. I just thought it was a really interesting idea. I'm not necessarily supporting it, but that actually life reflects the planetary conditions. Not the planetary, the planet itself, the whole lineage, the whole history of the biosphere. And it may not be so easy to just sort of be like, oh, just drop it over here and it all, you know, because the bacteria, even though they're individual examples of life, and I kind of believe this, the true unit of life, it's not DNA, it's not a cell, it's the biosphere. It's the whole community. Yeah.
That's actually an interesting field of study, is how when you arrive from one planet to another, so we humans arrive to a planet that has a biosphere, maybe a technosphere, what is the way to integrate without killing yourself or
the other one?
Or the other one. Let's just stick to biology. Like that. That's an interesting question. I don't know if we have a rigorous way of investigating that.
Because everything on life is, you know, has the same lineage. We all come from Luca, you know, the last universal common ancestor. And what you see is often in science fiction, people will do things like, oh, well, it's okay because like that that metabolism, that biochemistry is so different from ours that we can coexist because they don't even know each other, you know, right? That you know, and then the other version is you get there, you land, and instantly, you know, the nose bleeds and you're dead. Right? So it's
unfortunately, I think it's the latter.
Yeah, it sort of feels like a more alien kind of thing.
So as we look out there, according to the Drake equations we just discussed, it seems impossible to me that there's not civilizations everywhere. So how do we look at them? This process of SETI.
I have to put on my scientist hat and just say, my gut feeling is that dumb life, so to speak, is common. I am a little agnostic about, I can see ways in which intelligent civilizations may be sparse. Yeah. But until, you know, we got to go look. It's all armchair astronomy.
That's from a sort of rigorous scientific perspective. From my bro science perspective, it seems, again, smoking the aforementioned weed. It's
after the bong hit.
I mean, honestly, it's just it's really just it was impossible to me that there's not potentially dead but advanced civilizations everywhere in our galaxy.
Yeah, the potentially dead part, I think. Right, it could be that like making civilizations is easy; they just don't last long. So when we went out there, we'd find a lot of extinct civilizations.
Apex predators don't survive. Like they get better, and they die, kill themselves all somehow. Anyway, so just how do we find them?
Yeah. So SETI, Search for Extraterrestrial Technology, is a term that I am not fond of using anymore. I mean, some people in my field are, so I'm sorry, folks. But what I really like is the idea of techno signatures, because I think, you know, to me, SETI is first of all, intelligence. We're not really looking for intelligence. We're looking for technology. I mean, you know, and SETI, the classic idea of SETI is the radio telescopes, you know, and Contact, Jodie Foster with the headphones. That whole thing is still it's still active. There's still great things going on with it. But suddenly this whole new window opened up. When we discovered exoplanets, we now found a new way to look for intelligent civilizations or life in general in a way that doesn't have any of the assumptions that had to go into the classic radio SETI. And specifically what I mean is we're not looking for somebody sending us a beacon. You really needed that with the classic model for a bunch of different reasons. You had to assume they wanted to be found and they were sending you a super powerful beacon. Now, because we know exactly where to look and we know exactly how to look, we can just go about looking for passive signatures of the civilization, going about its civilizationing business, you know, without asking whether they want to be contacted or not. So this is what we call a biosignature or a technosignature. It is an imprint in the light from the planet of the activity of a biosphere or a technosphere. And that's really important. You know, that is why kind of the whole Gaia idea ends up being astrobiological, that biospheres and technospheres are so potent, they change the entire planet. And you can see that from 20 light years. So let's give an example of a biosignature to start off with, which would be a signature of a biosphere. Oxygen. right? On Earth, at least, we know that oxygen is only in the atmosphere because life put it there. If life went away, the oxygen, and particularly oxygen and methane, that pair, they would disappear, very quickly. They'd react away, they'd all be gone. So if you find a planet with oxygen and methane, that's a good bet that there's a biosphere there. Okay, what about technospheres? Technospheres, this is what, so I'm the principal investigator on the first grant NASA has ever given to do these kind of exoplanet technosignatures. NASA was kind of, for reasons we can talk about, NASA had gotten pretty gun shy about funding anything about intelligent life. But okay, what's an example of a technosignature? Well, one could be atmospheric pollution. I'm going to put pollution in quotes here because it doesn't have to be pollution, but gases like chlorofluorocarbons. So we dumped a huge amount of chlorofluorocarbons into the atmosphere by mistake. It was affecting the ozone, but we put so much in there that actually, this is one of the things we did. We did a paper where we showed you could detect it across interstellar distances. You could look at the atmosphere, look at the light coming from a distant planet, pass the light through a spectrograph and see the spectral lines, the spectral fingerprint of chlorofluorocarbons in an atmosphere. And that would for sure tell you that there was a technological civilization there, because there's no other way to make chlorofluorocarbons except through some kind of industrial process.
So you're looking for, in the case of the biosphere, you're looking for anomalies in the spectrograph.
I wouldn't necessarily call these anomalies. I'm looking for things that, for a biosignature, I'm looking for things that a geosphere, right? That just rock and air wouldn't produce on its own.
What kind of chemicals would life produce?
Right. And that's the interesting thing, right? So that's what, so we can use Earth as an example, right? We can say, look, oxygen, we know there would be no oxygen in the atmosphere if it wasn't for dimethyl sulfide, which is a compound that phytoplankton dump into the atmosphere. A lot of it. That's sometimes mentioned. And there was a paper that somebody wrote where it was like, well, we're not saying we see it, but there's a bunch of noise in the spectra right there. So there's a whole list of things that Earth has done that are in the atmosphere that might be biosignatures. But now we're reaching an interesting point. The field has matured to the point where we can start asking about agnostic biosignatures, things that have nothing to do with Earth's history, but we think that would still be indications of this weirdness we call life, right? What is it in general that life does that leaves an imprint? So one of these things could be the structure of the network of chemical reactions. That biology always produces very different chemical networks, who's reacting with who, than just rock and water, right? So there's been some proposals for networked, biosignatures. Information theory. You can try and look at the information that is in the different compounds that you find in the atmosphere, and maybe that information shows you like, oh, there's too much information here. There must have been biology happening. It's not just rock. Same thing for that's what we're working on right now. That for technosignatures as well.
So how do you detect technosignatures?
Okay, so with technosignatures, I gave the example of chlorofluorocarbon. Yeah. So that would be an example of, and again, that one is a non-agnostic one because we sort of like, oh, we produced chlorofluorocarbons, maybe they will, right? And there's solar panels, right? You can actually, the glint off of solar panels will produce the way the light is reflected off of solar panels, no matter what it's made out of, actually. There was a paper that Manasvi Lingam and Avi Loeb did in, I think it was 2017. We've just followed up on it. That actually could act as a technosignature. You'd be able to see in the reflected light this sort of big jump that would occur because of city lights, artificial illumination. If there's really like, large scale cities like, Coruscant in Star Wars or Trantor in the Foundation, those city lights would be detectable, the spectral imprint of those across 20, 30 light years. So, our job in this grant is to develop the first ever library of technosignatures. Nobody's really ever thought about this before. So we're trying to come up with all the possible ideas for what a civilization might produce that could be visible across, interstellar distances. And are these good ones, or is these ones going to be hard to detect or such?
City lights. So if a planet is all lit up with artificial light across 20 to 30 light years, we can see it.
Yeah. If you looked at Earth at night from a distance where, looked at its spectra and you had sensitive enough instruments, you'd be able to see all the sodium lights and the reflected light off of, they bounce off the ground, right? That the light bounces off the ground. So you'd convolve the sodium lamps with the reflected spectra from the ground, and yeah, you'd be able to see that there's city lights. Now, increase that by a factor of 1,000. If you had a trantor, and you'd be able to detect that across interstellar distances. Thomas Beatty did this work, who's now working with us.
What do you think is the most detectable thing about Earth?
Wow, this is fun. We just have a Sophia Sheaf, who's part of our collaboration, just did a paper. We did Earth from Earth. If you were looking at Earth with Earth technology for a bunch of different technosignatures, how close would you have to be able to detect them? And most of them turn out to be, you'd have to be pretty close, at least out to the Oort cloud. But actually, it is our radio signatures still that is still most detectable.
By the way, when you said you had to be pretty close and then you said the Oort cloud, that's not very close, but you mean like from an interstellar perspective.
Interstellar distance. Because the real question, we really want to know is like, I'm sitting here on Earth, I'm looking at these exoplanets. Yeah. The nearest star is 4 light years away. So that's like the minimum distance. So if I'm looking at exoplanets, what kind of signals could I see?
What is detectable about Earth with our current technology from our nearest solar system?
Oh my God, there's all kinds of stuff. Well, like the chlorofluorocarbons, you can see Earth's pollution, and I think city lights you had to be within the solar system.
If they do direct imaging of Earth,
they're going to need much more powerful. Yeah. But let me tell you let's talk about direct imaging for a moment, because I just have to go on. This is such a cool idea, right? So what we really want, and the next generation of space telescopes and such, is we're trying to do direct imaging. We're trying to get an image of a planet separated from its star to be able to see the reflected light or the actual emission from the planet itself.
Yeah, by the way, just to clarify, direct imaging means literally like a picture.
A picture. But the problem is that with even with the thing that's going to come after JWST, it's going to be a pixel, right? You're not going to get any kind of resolution. You'll be able to get the light from it, which you'll be able to pass through a spectrograph, but you're not going to be able to take a picture. But there is this idea called the Solar Gravity Lens Telescope. I think that's what it is. And the idea is insane, right? So their general relativity says, look, massive bodies distort space. They actually curve space-time. So the sun is a massive body. And so that means that the light passing through the sun gets focused like a lens, right? So the idea is to send a bunch of telescopes out kind of into the Oort cloud and then look back towards the sun, towards an exoplanet that is directly behind the sun, but is, in the direction of the sun. And then let the sun act like a lens and focus the light onto the telescope. And you would be able to get, and they've done, it's amazing. Like this idea is insane. They'd be able to get, if everything works out, 24-kilometer resolution. You'd be able to see Manhattan on a exoplanet. And this thing, it sounds insane, but actually, NASA, the team has already gotten through like sort of 3 levels of NASA. There's the NASA program for like, give us your wackiest idea, right? And then the ones that survive that are like, okay, tell us whether that wacky idea, is even feasible. And they're marching along. And the idea is that like, they even have plans for how you'd be able to get these probes out into the Oort cloud on relatively fast timescales. You need to be about 500 times as far from the sun as Earth is. But right now, everything looks like the idea seems to hold together. So probably when I'll be dead, but when you're an old man, it's possible that something like this, could you imagine having like, that kind of resolution, a picture of an exoplanet down to, kilometers. So I'm very excited about that.
I can only imagine having a picture like that, and then there's some mysterious artifacts that you're seeing.
Yeah.
I mean, it's both inspiring and almost heartbreaking that we can see. Like, I think we would be able to see a civilization where there's like a lot of scientists agree that this is very likely something, and then we can't
get there. But again, this is the thing about being long-lived. We've got to get to the point where we're long-lived enough that, so let's say we found, like, this is what I always like to, let's imagine that we find, say, 10 light years away, we find a planet that looks like it's got technosignatures, right? It doesn't end there. Like, that would be the most important discovery in the history of humanity. And it wouldn't be like, well, okay, we're done. The first thing we do is bigger telescopes to try and do those imaging, right? And then the next thing after that, we plan a mission there, right? We would figure out, like with breakthrough Starshot, there was this idea of trying to use, giant lasers to propel small spacecraft, light sails, almost to the speed of light. So they would get there in 10 years and take pictures. And so if we actually made this discovery, there would be the impulse, there would be the effort to actually try and send something to get there. Now, we probably couldn't land, but so maybe we'd take 30 years to build, 10 years to get there, 10 years to get the picture back. Okay, you're dead, but your kids are, so it becomes now this multi-generational project. How long did it take to build the pyramids? How long did it take to build the giant cathedrals, right? Those were multi-generational projects. And I think we're on the cusp of that kind of project.
I think that would probably unite humans.
I think it would play a big role. I think it would be helpful. I mean, human beings are a mess, let's face it. But I think having that that's why I always say to people, discovery of life, of any kind of life, even if it was microbial life, it wouldn't matter. That to know that we're not an accident, to know that there is probably, if we found one example of life, we'd know that we're not an accident and there's probably lots of life and that we're a community. We're part of a cosmic kind of community of life. And who knows what life has done, right? We don't really, all bets are off with life.
Since we're talking about the future of telescopes, let's talk about our current super sexy, awesome telescope, the James Webb Space Telescope that I still can't believe actually worked.
I can't believe it worked either. I was really skeptical. I was like, okay, guys, all right, sure.
We only got one shot for this incredibly complicated piece of hardware to unfold. So what kind of stuff can we see with it? I've been just looking through different kinds of announcements that have been detected. There's been some direct imaging.
Yes, like a single pixel.
The kinds of exoplanets we're able to direct image, I guess, would have to be hot,
usually far away from the, reasonably far away from the star. I think JWST is really kind of at the hairy edge of being able to do much with this. What's more important, I think, for JWST is the spectra. And the problem with spectra is that there's not sexy pictures. It's like, hey, look at this wiggly line. But be able to find and characterize atmospheres around terrestrial exoplanets is the critical next step. That's where we are right now. In order to look for life, we need to find planets with atmospheres, right? And then we need to be able to do this thing called characterization, where we look at the spectral fingerprints for what's in the atmosphere. Is there carbon? Is there carbon dioxide? Is there oxygen? Is there methane? And that's the most exciting thing. For example, there was this planet K2-18b, which they did a beautiful job getting the spectra. And the spectra indicated it may be an entirely new kind of habitable world called a Hycean world. Hycean meaning hydrogen ocean world. And that is a kind of planet that it would be kind of in the super Earth sub-Neptune domain we were talking about, maybe 8 times the mass of the Earth. But it's got a layer of hydrogen, of an atmosphere of hydrogen. Hydrogen is an amazing greenhouse gas. So hydrogen will keep the planet underneath it warm enough that you could get liquid water. You can get a giant ocean of liquid water. And that's an entirely different kind of planet that could be habitable planet. It could be a 60-degree warm ocean. So the data that came out of JWST for that planet was good enough to be able to indicate like, oh yeah, you know what? The models, from what we understand about the models, this looks like it could be a Hycean world.
And it's 120 light years away from Earth.
Yeah. And so isn't that amazing? It's 120 light years away, but we can see into the atmosphere. We can see into the atmosphere so well that we can be like, oh, look, methane. Methane was a 5 sigma detection. Like you knew that the data were so good that it was like the gold standard of science.
What about detecting maybe through direct imaging or in other ways, megastructures that the civilizations build?
You know what's great about megastructures is, first of all, it's fun to say. Who doesn't want to say megastructure? Alien megastructure, right? Every morning I'm looking for an opportunity to say that. So the example of this is the Dyson sphere, right? Which is amazing because, it was literally 1960 that this idea came up.
Can you explain the Dyson sphere?
Yeah, the Dyson sphere. So Freeman Dyson, one of the greatest physicists ever, who was very broad-minded and thought about a lot of different things. He recognized that, when as civilizations progress, what they're going to need is ever more energy to do ever more, amazing things. And what's the best energy source in a solar system? It's the star, right? So if you surrounded the star with solar collecting machines, sunlight collecting machines, and the limit of this would be to actually build a sphere, an actual sphere around your star that had all solar panels on the inside. You could capture every photon the star produced, which is, this insane amount of light. You would have enough power now to do anything, to re-engineer your solar system. So that was a Dyson sphere. It turns out that a Dyson sphere doesn't really work because it's unstable, but a Dyson swarm and that's really what he meant. You know, this large collection of large orbiting structures that were able to collect light.
Yeah, so he didn't actually mean a rigid
Right.
sphere structure.
Yeah.
He basically meant a swarm. So
Yeah.
that, like you said, in the limit basically starts to look.
People started to say, yeah, it was like a sphere. And we actually almost thought we might have found one of these back with Bajoyan's star. We saw, you know, the way we detect planets is through the transit method, where the planet passes in front of the star and there's a dip in the starlight. It's a little eclipse, basically. And we know exactly what they should look like. And then with this one star, there were these really weird transits where like it was like this little dragon's tooth, and then there'd be another one and another one and another one, and then nothing, and then three more. And in the paper that was written about this, they suggested they went through the list of, it could be comets, could be chunks of a broken up planet, and it could also be an alien megastructure. And of course, the news picked up on this, and like everybody's, news feed the next day, alien megastructures discovered. Turns out, sadly, they were not alien megastructures. They were probably gas or dust clouds. But it raised the possibility, like, oh, these are observable, and people have worked out the details of what they would look like. You don't really need direct imaging. You can do transits, right? They're big enough that when they pass in front of the star, they're going to produce a little blip of light, because that's what they're supposed to, right? They're absorbing starlight. So people did have worked out like, well, a square one or a triangular one.
But that wouldn't be a Dyson sphere. That would be like one object.
One object, right? Which is what if it's a swarm, you'd expect like the light to be like blinking in and out as these things pass in front of, if you've got thousands of these, much of the time they'll be blotting out the star. Sometimes they won't be. Right. And so you're going to get an irregular sort of signal, transit signal.
Yeah, one you wouldn't expect from a star that doesn't have anything.
Exactly. Or just a planet, right? Or a couple of planets. There'd be so many of these that it would be like beep, beep, blip, 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 blip.
And that usually doesn't happen in a star system because there's only just a handful of planets.
That's exactly what it is. Everything's in a stable solar system, you get a handful of planets, 5, 10, that's it probably, and nothing else. So if now suddenly you see lots of these little micro transits, you're telling you there's something else that's big enough to create a transit, but too many of them, and also with an irregular shape, the transit itself, that these could be megastructures.
How many people are looking for megastructures now?
Well, the main groups looking for megastructures are, again, Jason Wright at Penn State and collaborators. The way they're looking for it, though, is for infrared light, because, the second law of thermodynamics says, look, if you capture all of this starlight, you're going to warm up your thing's going to warm up and emit an infrared. There's going to be waste heat and waste light from this.
That feels like a louder, clearer way to detect it.
Right. And that's actually, Dyson, that's actually why Dyson proposed it. He wasn't really proposing it because like he was saying, this is what civilizations are going to do. He proposed it because he was like, oh, we want to start looking for alien civilizations. Here's something that would have a detectable signature. So Jason and company have done, pretty good searches. And recently they made news because, they were able to eliminate a lot of places. No, these are not Dyson spheres, but they did have a couple that were like anomalous enough that they're like, well, this is kind of what it would look like. It's not a detection. And they were saying they would never say it's a detection, but they were not non-detections.
They're potential candidates.
Potential candidates, yeah.
Love it. We have megastructure candidates. That's inspiring. What other megastructures do you think that could be? I mean, that's Dyson spheres about capturing the energy of a star.
Yeah.
Or there could be other.
Well, there's something called the Clark belt, right? So we have a bunch of satellites that are in geosynchronous orbit. Mm-hmm. Nothing naturally is going to end up in geosynchronous orbit, right? Geosynchronous orbit is one particular orbit that's really useful if you want to beam things straight down, or if you want to put a space elevator up, right? So there's this idea that if, a civilization becomes, advanced enough that it's really using geosynchronous orbit, that you actually get a belt, something that would actually be detectable from a distance via a transit. There's been a couple papers written about the possibility of these Clark belts, densely occupied Clark belts, being a mega structure. It's not as mega as a Dyson swarm, but it's, kind of planetary scale.
You think it's detectable, Clark belt?
It could be. I mean, like in our list of techno signatures, it would be down there. But it would be, again, if you had an advanced enough civilization that did enough of this, it would certainly, you'd have a Clark belt. And the question is whether or not it's detectable.
Yeah, probably Dyson sphere is that's the more exciting.
That's the go-to one.
Yeah. Speaking of the Dyson sphere, let's talk through the Kardashev scales.
Right.
What is the Kardashev scale and where are humans on it?
Right. So the Kardashev scale was the same time. This is this golden age of SETI, like kind of like 59 to 65 when it just starts. Like this is, Frank Drake has done his first experiment. People are like, oh my God, this is even possible. And so people are just throwing out these ideas. And as I, said in the book, science is conservative. And what I mean by that is it holds on to its best ideas. So Kardashev comes up with this idea that, look, again, it's always about detectability. If we're looking for civilizations, we should think about what are the natural stages, natural in quotes, that a civilization goes through. And he was thinking in terms of energy use, which I like a good physicist. So he said, look, the first hurdle in terms of energy or threshold that a civilization will go through is using all the starlight that falls onto a planet. He called that a type 1 civilization. In whatever way you're doing it, some large fraction of the starlight that falls on your planet you're using for your own ends. The next would be to use all the starlight there is from that star, right? So that's the Dyson sphere. So Dyson had already proposed his idea of the swarm, and Kardashev was picking up. So that's a type 2 civilization. Type 3 is galactic scale, a civilization that could use all the starlight in a galaxy. Right. So where are we now? Remarkably, on a log scale, we're at 0.7 of a type 1.
So we're not even type 1.
No, we're not even type 1. But according to, there was a paper written by a group that said, if we continue on our path, we'll be at a type 1 at around 2,300.
2,300.
Yeah.
So this is on a log scale.
Yeah.
So 0.7. So type 1 is about 10 to the 16th watts. Type 2 is 10 orders of magnitude larger than that, 10 to the 26th watts. And I think estimate for the galaxy is another 10 orders of magnitude.
Yeah, because there's 100 billion stars. Yeah.
So that's a lot.
That's a lot of energy.
Do you think humans ever get to type 1?
I think, that there's a problem with type 1, which is that, we already know about climate change, right? The effects of our harvesting energy to do the work of civilization is already changing the climate state, right? And that's something that, Kardashev couldn't have recognized. When there's the first law of thermodynamics, right, which is just about energy, the different forms of energy. Then there's the second law, which is about when you use that energy. And Kardashev wasn't thinking about the second law. If you get all that energy and you use it, there's waste heat. You don't get to use it all, right? Second law tells you that if, I have a tank of gasoline, I can only use a certain fraction of the energy in that tank, and the rest is going to go to heating up the engine block. So that second law tells you that, you can only use so much energy before the climate state is like, sorry, is going to change on you. So there's a way in which we probably can't get to a type 1 without devastating the Earth's climate. So we're probably going to have to figure out. The most important thing actually here is probably, this is why space becomes so, the colonization or settlement of space. If we have an idea that we've been working on for a while called service worlds, right? That at some point you probably move a lot of your industry off world, right? We've got Mercury, for example. There's nothing on Mercury. There's no life on Mercury. Why don't you put your energy harvesting there, right? Because you can't mess with the biosphere. The biosphere is more powerful than you are, right? And so so there's limits to how much energy we can harvest to do work on the Earth without really adversely affecting the biosphere.
It does seem that the best response to the climate change is not to use less technology, but to invent better technology and to invent technology that avoids the destructive effects.
This is the frontier where you are. And that was the topic of my last book, Light of the Stars. It's like you have to do the astrobiology of the Anthropocene. You have to see the transition that we're going through now of the Anthropocene on a kind of planetary astrobiological framework. And, that paper we were talking about with the 10 billion trillion worlds, that was actually in service of the work I was doing for this other book, where I wanted to know how often do you go through an How often, does every technological civilization trigger its own planetary crisis, its own climate Anthropocene crisis? And the answer we actually came up from doing models was yeah, probably. Mm-hmm. And then the question is, are you smart enough to figure out how to readjust what you're doing technologically so that you're not, that all boats rise, right? You want to figure out how to do this so that the biosphere becomes even more productive and healthy and resilient. So yeah, right. It's the kind of technology. I think there's probably absolutely limits on how much energy you can use, but how do you use that energy? And then also, yeah, getting off planet eventually. If you want to use 10 times more energy than that, you're not going to do it on world.
So how do we detect alien type 1, 2, and 3 civilizations? So we've been kind of talking about basically type 1 civilization detection.
Yeah. Right.
Maybe with the Dyson sphere, you start to get like a little bit more type 2. But it feels like if you have a type 2 civilization, it won't be just the Dyson sphere.
Right.
It feels like that just for the same reason you mentioned, climate change, but now at the star system level, they're probably expanding. Right. So how would you detect a type 2?
How about propulsion plumes? Right? If you're expanding,
Nice.
no,
great.
I literally
That's
just
great.
put in a NASA proposal now.
Nice.
Thomas Beatty, who's joined us he's at the University of Wisconsin, has an idea to look for plumes. Right? If you have a solar system wide civilization, right, and you got space truckers going back and forth, right, from Mars to they're doing the Enceladus run. They're accelerating and decelerating the whole way there, right? If you want to get to Mars in a couple weeks, you have your fusion drive on the entire way out there. You flip and burn and have it on, so you're also always have gravity. You have thrust gravity. So would those plumes be detectable? Because now you've got spaceships going all over the place, and the odds that the plume is going to cross your field of view could become pretty high. So yeah, I think that's a good way of looking for. That's one idea. Of looking for, large scale interplanetary, which is kind of like when you're getting to a type 2. Another possibility is looking for the tailings of asteroid mining. This was an idea. It was a group at Harvard Smithsonian that, to be able to look for if you're really chewing up asteroids to build space habitats, there'd be dust particles left around, and would they look different from just, say, the dust, from just regular collisions?
So pollution of all different kinds.
And
trash also?
Okay, so trash is an interesting idea when you come to the actual solar system, right? There's a whole other field of technosignatures, which are things in the solar system. What if somebody came by 1 billion years ago, and left some stuff, right? So the Earth has been showing biosignatures for billions of years. And, a species like us looking at our level, looking at Earth, would have been able to know that Earth had life on it, had a biosphere for billions of years. So maybe somebody sent something by, a 500 million years ago. So this idea of looking, say, at the moon for artifacts that have been there for a long time is something that a number of people are doing. We're just working on a paper where we just calculated, this was super fun. We calculated how long would the lunar lander exist on the moon before micrometeorites just chewed it down, right? How long would you be able to land on the moon and go, oh, look, there's somebody was here and left some debris. So there's this process called gardening, which is just the micrometeorite, constant rain of micrometeorites, and that's where you get the lunar regolith, that fine powder on the moon, is because of this gardening. And it turns out it is literally hundreds of millions to billions of years.
Oh, nice.
That the lunar lander will be visible.
Oh, so we should be able to find artifacts.
Yeah, if there are artifacts and people have proposed doing this with artificial intelligence. We have, the moon has been mapped down to like a couple of meters with various probes, and all that data is sitting there. So why not use machine learning to look through all those things and look for anything that looks not like the lunar surface? And they did a test program where they gave the computer, sort of like, I don't know, 50 miles around the Apollo 11 or maybe it was the Apollo 17 site. And it instantly was able to pull out the lander.
I mean, the whole task of looking for anomalies, something that looks not like the lunar surface, you make it sound obvious, but it's not exactly obvious. Like anomalies is really not, detect something that doesn't look right about this room.
Yeah.
It's actually really difficult.
It's really difficult. And it's, what's cool, it's a really information theoretic kind of proposal. You really have to use information theory to say, like, what's the background? What's, how do I define something that I can say that looks weird? So,
yeah, maybe when you're looking at a spectrograph or something, like, it's still like, it's going to look really weird potentially. Like we're kind of hypothesizing all the things that humans would build.
Right.
And how do we detect that?
Right.
But there could be really weird stuff.
That's why there's this emphasis now on these agnostic signatures, right? So actually disequilibrium is a nice one. One way to define life is it is a system that is far from equilibrium, right? It's alive, right? Because as soon as it dies, it goes back to equilibrium. And so you can look at all chemicals in an atmosphere, even if you don't know whether these could be chemicals that you have no idea whether or not they have anything to do with life. But the degree of disequilibrium, the degree to which they show that atmosphere has not, the chemicals have not all kind of like just gone down to they've all reacted away to an equilibrium state. You can actually tell that in very general ways using what's called the Gibbs free energy. And that's kind of a signature. Like if you see an atmosphere that is wildly out of equilibrium, that indicates that there's something happening on that planet, biosphere or technosphere, that is pumping gases, into the atmosphere that is keeping the whole system from relaxing.
So is it possible we can detect anomalies in space-time?
Well, you could detect, and there's been some work on this, like with the Akubre drive, the proposals for warp drives, and we can talk about that later. I'm skeptical of those, but because it may really be possible you just can't go faster than the speed of light. But people have done work on what would be the signature of an Akubre drive? What would be the signature? Could you detect if you're using a drive like that, then you certainly are distorting space-time, which means any light that's passing by has gotten, its trajectory has gotten altered because it had to pass through the distorted space-time. So yeah, there are possibilities along with that. One of the funny things, I don't know if they've gotten past this, but somebody calculated the problem with the Akubre drive or this warp drive was that if you dropped out of warp, there would be this spray of gamma rays that would like sterilize any planet in front of you. So it's like, well, yeah, you probably don't want to do that, but that would be a great bios or techno signature. Another planet obliterated.
So you think it's not possible to travel fast than the speed of light?
I wouldn't say that. But what I think, if you look at the physics we understand, right?
Yeah.
Every possibility for faster than light travel really relies on something that doesn't exist, right? So the cool thing is Einstein's field equations, you can actually play with them. The equations are right there. You can add things to the, right or left-hand side that allow you to get something like the Akubre drive. That was a metric that, showed you like, oh, it's a warped bubble. It's a warping of space-time that moves through space-time faster than the speed of light, right? Because nothing can move across space-time faster than the speed of light, but space-time itself can move faster than the speed of light. But here's the problem with all of those proposals is they all need something. The thing you added, the little fictional term you added into the equations is something called exotic matter, and it doesn't exist. It's really just something we dreamed up to make the equations do what we wanted them to do. So, it's a nice fiction, but really right now, we live in this weird moment in history of the Great Acceleration, where like the technology we use now is completely different from the technology we used 10 years ago, is remarkably different from the technology from 100 years ago. But I remember playing Assassin's Creed, where everybody's like, what is it? It's 1200, and everybody's like, stab, stab, stab. And I was like, yeah, it's a great game. And then I got Assassin's Creed 2, and it was 300 years later, and everybody's like, stab, stab, stab. And it was like 300 years, and the technology hadn't changed. And that was actually true for most of human history, right? You used your great-grandfather's tools because there was no need to have any other new tools. And you probably did his job. So we could be fooled into thinking like, oh, technology is just going to go on forever. We're always going to find new advances, as opposed to sometimes things just flatten out for a long time. So you have to be careful about that bias that we have living in this time of great acceleration.
Yeah, but also it is a great acceleration, and we also are not good at predicting what that entails if it does keep accelerating. So, for example, somebody like Eric Weinstein often talks about we underinvest in theoretical physics research. Basically, like we're trying too hard for traditional chemical propulsion on rockets versus like trying to hack physics, sort of warp drives and so on, because it's really hard to do space travel. And it seems like in the long arc of human history, if we survive, the way to really travel across long distances is going to be some totally new thing.
Right.
So it's not going to be an engineering problem. It's going to be a physics problem.
Fundamental physics problem.
Fundamental physics problem.
Yeah, I mean, I agree with that in principle, but I think there's been, I mean, there's a lot of ideas out there. People, string theory, people have been playing with string theory now for 40 years. It's not like not like there hasn't been a lot of effort. And, and again, I'm not going to predict. I think it's entirely possible that we have, there's, incredible boundaries of physics that have yet to be poked through, in which case then all bets are off, right? Once you get sort of, fast interstellar travel, whoa, who knows what can happen. But yeah, I tend to be drawn to like science fiction stories that take the speed of light seriously. Like what kind of civilization can you build where like it takes, 50 years to get to where you're going and 50 years back? Like, so I don't know. I mean, yeah, there's no way I'm going to say that we won't get warp drives, but as of right now, it's all fictional. It's, it's barely even a coherent concept.
Well, it's also a really exciting possibility of hacking this whole thing by extending human lifespan or extending our notion of time, and maybe as dark as to say, but the value of an individual human life versus the value of life from the perspective of generations.
Yeah.
So you can have something like a generational ship that travels for hundreds of thousands of years.
Yeah.
And you're not sad that you'll never see the destination because you kind of have the value for the prolonged survival of humanity versus your own individual life.
Yeah. It's a wild ethical question, isn't it? That book I told you about, Aurora, I love the book because it was such a sort of inversion of the usual. Because, I love science fiction. I've read so many generation ship stories. And they get to that planet. The planet turns out to be uninhabitable. It's inhabited, but it's uninhabitable for Earth because, again, he has this idea of like, life is particular to their planets. So they turn around and they come back. And then when they land, the main character goes, there's still people who are, arguing for more generation ships. And she goes and she punches the guy out because she spent her whole life in a tube, with this. I thought that was a really interesting inversion. The interesting thing about we were talking about these space habitats, but if you really had a space habitat, not some super cramped, crappy, the usual version of a century ship, but if you had these like space habitats that were really, like the O'Neill cylinders, they're actually pretty nice places to live. Put a thruster on those, like why keep them in the solar system? Maybe space is full of like these sort of traveling space habitats that are in some sense they're worlds in and of themselves.
There's the show Silo, which raises the question of basically, if you're putting on a generational ship, what do you tell the inhabitants of that ship? You might want to lie to them.
Yeah.
You might want to tell them a story
that
they believe.
Right.
Because there is a society, there's human nature. There's like, how do you maintain homeostasis of that little society? I mean, that's a fascinating technical question, the social question, the psychology question.
The generation ship too, and which I talked about in the book, the idea of you talked about extending human lifetimes, or the stasis, the cryostasis, which is a mainstay of science fiction. You can be put to, you can basically put in suspended animation and such. None of these things we know are possible. But it's so interesting, and this is why I love science fiction, the way it seeds ideas, right? All these ideas we're going to talk about because they've been staples of science fiction for 50 years.
I mean, the whole field of cryogenics.
Yeah, where are we at with that?
Yeah, I wonder what the state of the art is for a complex organism. How long can you freeze and then unfreeze?
Right.
Maybe like with bacteria, you could do freeze and unfreeze.
Bacteria can last. This is the thing about panspermia, right? How long can a bacteria survive in a rock that's been blasted? If there's a comet impact across interstellar distances, that does seem to actually be possible. People have done those kind of calculations. It's not out of the realm of possibility. But a complex organism, multicellular, multisystemic, or multisystems, right, with organs and such.
Also, what makes an organism? I mean, it could, which part do you want to preserve? Because maybe for humans, it seems like what makes a personality. It feels like you want to preserve a set of memories. Like if I woke up in a different body with the same memories, I would feel like I would be the same person.
Altered Carbon. Have you? That's a great series. I think it's on Netflix. It's that's a really great series where that's exactly the idea of sleeves. Everybody's able to you can re-sleeve in another body, and it raises exactly sort of this question. It's not the greatest cyberpunk, but it's pretty good. It's got some great action sequences too.
As we get better and better advancements in large language models that are able to be fine-tuned on you, it raises a question because to me they've already passed the Turing test as we traditionally have defined it. So if there's going to be an LLM that's able to copy you in terms of language extremely well, it's going to raise ethical and I don't know, philosophical questions about what makes you you. Like what if there's a thing that can talk exactly like you, like what is the thing that makes you you? It's going to speak about your memories very effectively.
This leads us to, if we're going to get to the blind spot, I'm of the opinion, heretical in some camps, that the brain is not the minimal structure for consciousness. It's the whole body. It's embodied in me. Actually, in some sense, it's communities. Actually, so I don't. I mean, I could be wrong, but this is what this whole work that I did with Marcelo Gleiser and Evan Thompson, the philosophy of science, which is interesting because it leads to this question about right, oh, maybe we should just download ourselves into computers, right? That's another story that one tells. I'm super skeptical about those, but that's one of the narratives about interstellar travel is just like, and that anybody we meet is going to be a machine anyway, whether it's downloaded bodies or it's just going to be artificial intelligence. Like there's the whole idea of how long does biological evolution last? Maybe it's a very short period before everybody goes to, or the machines take over and kill you, or it's some hybrid.
What do you think aliens look like? So we talked about all the different kinds of biosignatures they might leave or technosignatures, but what would they look like when we show up? Are they going to have arms and legs? Are they going to be recognizable at all? Are they going to be carbon-based?
Yeah, so great question. And this question gets to the heart of thinking about life, right? About what life is. And this is the physical part of that. There's also sort of the informational part of it. Mm-hmm. But let's just talk about the physical part of it, which is, life, anything that we're going to call life is probably going to work on Darwinian evolution. That's the nice thing about Darwinian evolution. Just like we know the laws of physics are general, the laws of Darwinian evolution are kind of this logic, this basic mm-hmm. logic, that, anything we'd reasonably call life probably has to operate under these kinds of principles. And so, evolution is about solving problems that, to survive, that the environment presents. And the environment is always going to present these problems in physical and chemical terms so that you'd expect a kind of balance between what we call convergence, evolutionary convergence, and evolutionary contingency. Mm-hmm. So, if you got to move along a surface, a surface between, a hard surface and air, then the idea of some kind of jointed stick, right? Mm-hmm. Legs, makes sense that you're probably going to trigger that. If you look at Earth's history, multiple times, multiple lineages that had nothing to do with each other are going to solve the problem of getting towards energy sources using some kind of, a stick-like apparatus.
So that's about movement?
Yeah, so that's one problem that has to be solved. One problem that has to be solved is they got to get to food, right? Another problem is they got to get away from predators, right? You've seen wings. We've seen wings. The line that went through dinosaurs to birds involved wings. Insects evolved wings. Mammals evolved wings. If the gas is dense enough that a curved surface, if you move through the curved surface, it's going to produce lift. Yeah, there you go. Evolutional trip on that. So I think you can expect certain classes of solutions to the basic problems that life is gonna be presented with. Stay alive, reproduce. But one of the weird things about with the UFO things is that you always see oh, they all look like humans. They're just basically humans with, triangular heads. And that's where we get to contingency, right? So what we've been talking about is convergence. So you expect that evolution will converge on wings multiple times when presented with the problems that wings can solve. But contingency is accidents, right? That, you've got something that's evolving a certain kind of wing, a leathery wing, right? And then, the climate changes and they all die out. End of story. Or, an asteroid, total accident, asteroid hits. And so contingency, accidents play also a huge role in evolution. And one of the things that, lots of evolutionary biologists have talked about is the idea that if you ran the tape of Earth's history over again, would you get the same creatures? Now, Stephen Jay Gould was of the opinion that no way, that you wouldn't find anything on Earth that resembled any species today. They've done experiments actually on this with E. coli. You take a bunch of E. coli, you let them evolve for a while, you take a bunch of them out, freeze them, let that population continue to evolve. The other one's frozen. Now start it over again with the frozen. Mm-hmm. And it seems to be that contingency tends to win. Right? The contingency, At least from what we can tell. I mean, that's not a hard result, but in those experiments, what you find is that accidents really do matter. So the idea, and this is important. So yes, you should expect legs or jointed sticks. How many joints they're going to be? Anybody's guess. Do you expect humanoids, things with a sensing apparatus on top of a shoulder with 2 arms and 2 legs? That's probably a pretty random set of occurrences that led to that.
I guess what is a brain versus the nervous system? Like, where is most of the cognition computation going on?
Yeah.
You could see that in organisms. Like, actually, I don't know how the brain evolved. Like, why does it have to be in one place?
Doesn't have to be. So my favorite word of the day is liquid brains, right? This idea of distributed cognition, which fascinating idea. And we've come to understand how much distributed cognition there is. Obviously, eusocial animals like termites, etc., and ants, that's an example of distributed cognition. The organism is the whole colony. This is one thing that's been really interesting in the state of the study when we cut to for aliens, is that what we've come to recognize is that human intelligence, it's not actually, it's been the kinds of things that go into intelligence are distributed all across the biosphere. Lots of different examples of things show various pieces of what we have. Jason Wright will describe it as like a deck of cards. The cards are all there. We got the hand that actually led to the kind of technological progress that we see. But the kinds of, the basic idea of using tools, the basic idea of recognizing each other eye to eye, all the things that we define as intelligence, you can find many places in many other places across, many other lineages across the earth. So they could be very, very different.